Bonjour à toutes, à tous. Pour rappel, en début de conférence, les rendez-vous du mardi sont une tradition de l'école de Marne pour introduire des architectes, des figures de l'architecture, des postures, des thèmes, mais c'est aussi l'occasion pour nous de mettre en question la profession, la pratique de l'architecture sous ses différentes formes. Alors ceci n'est pas une leçon, ni une conférence, mais un cycle de rencontres et de discussions organisés avec Anne Clépal autour de la notion d'auteur. Nous vous présentons des bureaux, agences, ateliers, architectes qui travaillent le projet en se créant un environnement de pensée incluant différentes disciplines. Ce travail de pratique architecturale partagée, hybride et collective et inventive permet-il d'engager une fabrique de projets plus adaptée à notre climat d'incertitude, à nos manières d'habiter la transformation du monde, à engager l'architecture dans une direction qui dépasse notre propre champ. Pour questionner cette notion d'auteur, nous mettons en présence chaque semaine un architecte, cette semaine Amin Taha, et son traducteur, l'ingénieur et architecte Klaas De Rycke. Traducteur d'une conception, traducteur d'une pensée, d'une expérimentation, mais l'architecte est peut-être lui-même le traducteur d'une conscience structurelle. Lost in Translation est le titre de ce jour, ponctué d'un point d'interrogation. Si nous étions la semaine passée avec Pierre Ebling dans un atelier ou laboratoire, nous sommes cette semaine avec Amin Taha dans une société d'actionnariat salarié, Group Work, dont Amin en est le président. Une société qui lui permet de ne jamais devenir autocrate. C'est une structure de codépendance qui repose sur le partage des idées, mais aussi des biens de cette agence. Amin Taha, architecte et enseignant, actuellement à la faculté d'architecture du Royal College of Art de Londres. Il est également professeur invité à Yale et Harvard aux États-Unis. De nombreux titres et réalisations que vous connaissez et nous intéressent aujourd'hui pour son approche de la façon de construire. Quelle place à l'approche constructive dans le processus d'élaboration du projet? Pourquoi construire en pierre a-t-il un impact politique et culturel? Comment expérimenter pierre et bois pour atteindre un bilan carbone négatif? Construire de façon plus économique et éthique conduit-il à revenir au New Stone Age? Si Amin Taha est ici aujourd'hui, c'est grâce à Klaas De Rycke, qui n'a en réalité aucune réalisation en commun, mais un intérêt commun porté sur la remise en question et l'évolution du mode constructif. Klaas De Rycke est ingénieur-architecte. Il rejoint Bollinger+Grohmann en 2003 à Francfort, puis à Paris en 2005 pour accompagner Dominique Perrault sur le Théâtre Mariinskiy. En 2007, il fonde l'agence parisienne et dirige également depuis 2015 celle de Bruxelles. Auteur et conférencier, professeur associé à l'ENSA Versailles et professeur invité à l'UCL Bartlett School de Londres. Lost in Translation, we are delighted that you have accepted the invitation. Thank you so much. You have the floor.
Thank you. Merci, Philippe. The conference will be in English, so if that's okay. If you have any questions, please raise your hand. So. No worries, you can easily ask us. So when we got the invitation for the conference, we actually talked for a couple of months already to see with whom we would do this stand-up comedian show. No, it's not a comedian show, no, but so we thought like, with whom can we talk? And for us, this kind of talks is also a bit putting yourself into doubt and to question, a bit of a challenge. So to question your work yourself, and also that of your colleagues with whom you work basically together. So in that sense, we talked with Amin, like how can we do it together, whether we have no projects together, but we do certain stuff that are similar or where we work together. So we thought, let's challenge each other. So what happened, we met yesterday evening and we had the both presentations, and this morning I asked my team to mix the both presentations. So it's gonna be a bit of a surprise for the two of us as well. So we might have to jump some slides. So I don't know the total amount of slides either. So if there's something, we will find out together with you. So it's a bit of a journey for ourselves, but we have to put ourselves a little bit of these things. Since the conference, we already talked about it quite a long time. We took this image because it's typically one of a professor that you have here at the school. And that's one of these projects where we worked on a very long time. It's a very, very tiny project, 400 square meters for only 500,000 euros, so it's quite cheap. And it's very complex. And that's with the one project I wanted to explain the lost in translation. But before that, one colleague gave me this image at some point. And I don't totally agree, but possibly you went through this already yourselves on Instagram or somewhere. So this is apparently how is perceived the way of how a client, architect, engineer and builder work together. And at some point after construction, your nice concept idea, as you are all students now, you will face yourselves in some years from now. I hope it's going to stay to the original conception, right? But it might be that you come finally with a project that is not entirely what you imagined. So in order to challenge that view, that's what we and you have as a task for tomorrow. And this is why I thought it would be very interesting not to just purely look at the way how an engineer perceives, neither just the architect, because we're both translators and not so you have this word in English, it's rather an interpreter, which I find quite much better than just purely translating, because by now all the AIs are pretty well translating stuff, but an interpreter is quite much more than just a simple translation. I think this is a bit what we want to talk about today. So we've foreseen, I first give you like, what about the title, why this title? And we'll show you a little bit what we want to try to go through today after this little introduction. So here, this is the work from Ido Avisar with Hideyoki Nakayama. And this is where the competition came in. So a very small extension for somebody, a very famous artist back then, Frans Mazerel, who also made very nice pictures of France in the 1930s. And Thomas Mann is actually also writing about this guy. And it's a very small art center in Belgium. And the extension, an invited competition actually. And Ido and his team, they thought, let's make a circle, a bit like the original building, but then we make it so everybody's working under the same roof, but then there's special rooms, and that we can do by cutouts. Okay, fine as a concept. But they wanted to do the roof in concrete, so that you have the feeling that everywhere, everything is all the same at any single point. So there's no hierarchy. But since I'm not particularly a fan to do everything in concrete, just for pure ecological reasons, I thought, like, why not do it in timber, and also take the challenge to do it in massive timber. So you need to be careful about the length of the beams. So we took back a conception of the 1400s, more or less, a reciprocal system, and we proposed that to the architect, and they were wildly enthusiastic about it, so they let us work. What happened is that we used some of our genetic algorithms, so we have our own software, Caramba 3D, that is in Grasshopper. It's an open source, so you can use it. It calculates, but it also looks with genetic algorithms to propose things. So we made about 2.8 million different variants, from which we chose 200 that we showed to the architect, and then he came back with different parameters. And what I found so beautiful with this, not the project on sich, I find it already quite spectacular, but in the way that we had to discuss is through the algorithm that we had to build. So each of yourselves have trained already your algorithm so far from your birth to today, and you're all different. So when you do a group work, as is the name of Amin, you all come in with your different algorithms. And the way you want to bring them together is about exchanging on parameters that you want to test. So those are the ones that you have in common, the common ground that you are trying to have. And this work with the computer you have to give it specific task. So once you do that, you also have to convince each other which arguments are the ones that you want to test. So you really are obliged to communicate and to interpret what the person in front of you is telling you. Because a computer can give a result for anything, but it can be really bullshit also, because it's just not the right way we were looking for. So I thought this way of working, I will not go into the project itself. It went quite complex in the end, but we also know very well how to construct, and we know the contractors, so all the information from building details, this comes from the engineer, and we had to comply with the ones that are actually about aesthetics, that are about acoustics, functionality. So if you bring those all together, it's like, how do you bring these two different matrices together, right? Like an algorithm that you have to build and generate together. And that for me was the initial setup, why I thought about this series about lost in translation. How do you do it? Because that, if we see the challenge of today, is that only since 200 years the French invented new schools like the Pont et Chaussée to really make happen or make engineers work on their own. But how do you bring those things together to face the challenges of tomorrow? So this is some ideas. And so now, so look, I'm discovering this now, and you as well. I think the list of projects, oh, okay. We got some time, huh? So if you fall asleep, just ask your neighbor to wake you up. And so I see we have a bit of a theoretical part. I thought, like, what is your context? And today we also decided, because we both work on a lot of different projects, so, but I thought for what is happening today in your context, it might be interesting to, one, have an architect from Great Britain, because Brexit, they're out of the European Union, so not follow the rules. And second is also, maybe it gives another view on some of the professors here in your school already work with natural stone. So I think Thibaut Barrault is also here in the school, no? I think. So he said, like, why not give another perspective on it? So we're coming from outside, we're a bit the terrorists at the moment. And for that, we started with some context to check what is your situation. So we tried to understand where we are today, as you have to do all the time. Tacit versus explicit, we're going to explain it to you. Experimental or experiential pedagogy, so the world of making, that's to get to what you guys have as a role, also with this school, what is happening. And then from there, we developed through some projects what we understand, so the theory. Well, maybe we will not do them all, no? Amin? We'll see. It's a bit, okay. Maybe we can jump to the conclusion then. It's, so that's where we tried, no? We tried a little bit, I'm not sure. We were both not sure if it's better or worse. We can vote on it after the session. But so that's what we try. We also said, should we actually see what we have in common? So we did one test and then we stopped because it was bricks, because we're both from a brick country somehow. I'm Belgian, by the way. So, and you're from the UK. And so we have some things in common, but not everything. So let's see where that brings us now. The world of figures, context. I think what I started with, and Amin as well, it was very funny to see because we do build up our conferences a bit similar in that sense. So we really try to understand why we do buildings the way we do it. And so one of that is for you guys at the moment, this is the daily story you are hearing, right? About your carbon footprint, the life cycle, about the building industry as being the one that is responsible for 30% of the global CO2 emission. So actually you are people with a certain impact. You are not to underestimate what is the impact of what you guys will do in the future. Do you still have the right to build actually? Should be the first question probably. And maybe for France we don't need to do it anymore. But there's enough countries in the world where you still will need to build. And so even for that, you guys have the power in your hands for the future. So these are the discussions. I hope you all have this already in your minds, embodied and operational carbon. I think those are concepts, nothing new for anyone, right? No, it's fine, yeah. So what we are trying to work on, like this operational carbon, okay, this already improved quite a lot and we're still doing it, maybe with a bit too much of technology, so we might want to skip and go back to more natural ventilation, all these things. I think that's all very smart. The one we can actually really work upon is also the embodied carbon. That's one where you really, especially since we talk between an engineer and an architect, I think that's really easy to talk about it. There's other figures that I got out of the press. 50% of the global material consumption. Again, I'm a Belgian, and Belgium has the 2 biggest dredging companies in the world. So just to give you an idea, that's the people that take out sand of the ocean. So they get paid for that. Like they get paid to get the sand away so that the bigger boats can come in. And then they sell the sand again to somebody else. So they get paid twice. It's a brilliant concept. So it's very Belgian, I think. So So mining of sand per year, it's too much. We can't do with that. Building industry is responsible for 54% of the waste per year also. So it's a bit of a dirty business, what you guys are learning at the moment. And this, see, this is in other figures, what you had brought, I think, no? I mean, it's a bit similar.
So, yeah, hello. Thank you. Okay. So most of you would have heard of LEED, BREEAM, Passive House, and so on. Now, most of those are created post-oil crisis, so this is the 1970s, specifically, all about energy consumption, or the drop in energy consumption. So their measure, you can achieve platinum, diamond, the best possible criteria under BREEAM, LEED, and so on, by reducing your energy consumption. Just thinking about using timber without using it will get you a bonus point. It doesn't measure the embodied carbon of your material choices. More recently, and this is not, when I say more recently, this is 2017, the universally adopted, globally adopted measure for the embodied carbon of your building, I'm trying to remember that number, EN15978, which breaks down, as Klaas was saying, your embodied carbon into materials and the construction, in red, in yellow, the operational carbon, and then in green, when you demolish your building and the energy it takes to demolish and reuse those materials, if they're being reused. Yeah. Now, actually, every year, the percentage of those changes. So the operational carbon, from when I was your age, being educated, used to be about 80% compared to the 80 or 90%, depending on the type of building, to what it is today. So 2017, they were estimating it was going to be about 40%. So the materials, their construction, their transportation, and their demolition is roughly 60% today. Why do you think operational carbon is half of what it used to be when I was your age? Anybody? Should I point at somebody? Anybody? Should I point at one of your professors? Anyway, it's because we insulate buildings better compared to the 1970s and early 80s. We have double glazing, triple glazing, heavy insulation, and the equipment is much more efficient. So hypothetically, we could reduce our operational carbon more and more and more, but you can't change the nature of those materials. Not a lot. Yeah. So steel, concrete, bricks, other materials still have to be made, extracted from somewhere, processed and made. I don't know if the next slide, yeah, there we go. At the same time, the University of Bath and the British Services Research Institute created something called ICE, the Inventory of Carbon and Energy. So they listed all the materials that are normally used in construction. Here's only a few of them. From the worst performing, aluminium, polyester powder coated aluminium, all the way down to roughly sawn hardwoods. Yeah, we put them in order, so worst performing at the top, and give it color code. I don't know what it's like for you when you go to supermarkets here. Is it the same as the UK? Everything's color coded, high fat, high sugar. Yeah. Okay. So this is not about the lesson today. Is that, please take away, it's not about saying, I must just eat boiled cabbage from now on. I know we're in France, so we can speckle the boiled cabbage with some fried lardons, yeah, right at the top. Have some cigarettes, but clearly, if your shopping basket is always full of the red, I can see some of you are packing it full of the red, having a great time, great dinners, yeah. But you won't be around for long. While some of you, your dinner parties are terribly boring. Boiled cabbage. So it's just mixing it. So the takeaway is just mix those carefully. Can you see here? Is that visible? There's a minus here, isn't there? Carbon sequestrating. I'm hoping the education system in France is better than the UK, because you ask some engineers in the UK, I don't know, how's it carbon sequestrating? What does that mean? Everybody know what carbon sequestrating means? How timber is carbon sequestrating? Yeah? Excellent. Good, good. So the carbon is locked in, isn't it? As long as this thing is not burnt or put into landfill to rot, the carbon is locked in. The oxygen's out in the air. The day that you burn it, has a chemical reaction, pulls the oxygen in, out goes CO2. That's why it's minus, because it takes double the weight of CO2 to pull apart to make the same weight of the complex sugar that becomes your timber. So what is that? What's that thought experiment? What does that immediately tell you after class has told you you're actually being educated to become human rights criminals, making life worse for everybody? What does that tell you if you anyone? What's the thought experiment? If you make your building 100% out of timber, you've taken more CO2 out of the atmosphere by getting up, and drawing, and building. Yeah? But you can't make your building 100% out of timber, can you? The electrical wiring can't be timber, the plumbing, the glazing. So slowly but surely, you have to mix those materials. But if you start by default in the timberland, this area here, and slowly substitute your materials, hopefully you can still stay negative. Okay? What's the next one up? The first into positive. Stone. Now, the reason that we suggest stone is not for sentimental reasons, the past somehow fitting in with historic areas, but because the embodied carbon is so low. Why is it so low? Anyone? Shall I just point at somebody? You. Why is it so low? You don't know. That's definitely not why it's so low. You. Exactly. It's already made for you, below your feet, over millions of years ago. Yeah, most of it over millions of years ago. Travertine, like stalagmites and stalactites, is made every year. It's very recent. But otherwise, it's just made for you. All you have to do is cut it out the ground, ready to use. Yeah, and it's then the energy that you use to cut out the ground, transport it. Now in France, some of your quarries are already using electrical energy to cut the stone. And I've gone to one quarry. They say, I say, where's it come from? Nuclear. Well, it's practically renewable, isn't it? If you calculate the amount of energy they use to cut out a cubic meter of stone, what is it? It's almost nothing. So that calculation is using diesel equipment. So if you ensure the quarry is actually using electrical energy, it's next to zero. Okay? Why would you use stone instead of timber? Where would you use stone instead of timber? Somebody accidentally made eye contact with me. You. Where would you use stone instead of timber? Perfect. Foundation, superstructure. I mean, you can go up with timber and superstructure, but at some point, it makes no sense. You're using so much timber to go up tall, it makes no sense. You could be more efficient using stone. Okay? Foundations, maybe the external envelope to be very robust, and then some of your other materials. Okay. What about timber, though? People say, oh, if we use timber, I go on these conferences where there's normally an engineer in front of me, not you guys. I won't mention those engineers who say, if all of us decided to use timber, there'd be no woods left. All of it would disappear, forgetting that sustainable forestry is a real thing. It's already active. Europe is actually growing its forest faster than it's cutting them down. Why is that? It's a decision. Policy. So this is Slovenia, I think. Yeah. Anybody been to Slovenia? Yeah. Very nice place. 70% woodland. And they have a very, very straightforward policy. For every 100 trees we plant, we take 75 down. And those are normally about 80, 100 years old. That leaves room for new ones to grow. So the forest is always growing. Okay, going into your slides.
So second, in the line of what, so that's a bit your context. I hope we didn't say so much new stuff, but because that's where you're heading for, that's what is the challenge for you ahead. The one where we thought, and we share that vision, and which should be quite interesting, is tacit versus explicit. And what are we talking about? So tacit knowledge is something that you are learning by doing, something that was passed to you by a previous generation, like the master builders you would have for the churches. So I have a holiday place near Beauvais, and there's a cathedral in Beauvais. I think they let it come down 3 times, and they built for 200 years on it, and they never finished it. But there's some knowledge there, so these people knew certain things. Salut, ça va? Bah oui. Bien. So that tacit knowledge is something that has always been around. We're rapidly losing it also because we don't hand over this kind of knowledge so easily anymore. And if I look at people, this kind of farmer's knowledge, so I come from a farmer's family where people actually reconstruct their barns all the time with the same materials. They are recuperating. Le réemploi, it exists actually. These people, it's very pragmatical. And this is a bit what is, it already exists, but we never put it into the explicit knowledge. And what happens now is, if so many people want to build and we need to pass on knowledge, the guy that is on the construction site, how does he know exactly what to do? So he needs a manual. You need boundaries also and security margins so that we are sure that we will repeat in the same way to build things that will not fall down. And this is the task of also universities. That's why we do research, fundamental research, so that we can write codes that everybody keeps as much as possible to these codes. Because I don't believe much in codes, to be honest. I don't like them very much, that somebody gives boundaries. But they have the fantastic advantage. And in the last 150 years, many less buildings came down, like structural failings, than the previous centuries. So there is a certain reason why buildings became safer. Sometimes it goes a bit in the wrong direction, but this is where your task as academics, because you are at the university, we need to get that explicit knowledge out also. And if you look at it, like here, this was what people were building. So I travel a bit, so I try to really keep up to date. How did people really build? And usually it's because it's with materials that are locally sourced. It's also look at people, how they turn their buildings to the right orientation because they knew where the winds were coming from. Nowadays, we build buildings everywhere. And I just was working on a regular house. And we need to make pile foundations of 40 meters deep for a regular house. Does that sound really reasonable? I don't think so. So we should decide that we should not build there. And this is what people were doing. When it was always flooding, you would not build at the same place. And at the moment we are building in many places where we should not build. So this kind of knowledge, building up like here, this is the typical houses that you would have. This is fantastic, massive timber. You can replace every piece. If it's rotten or something, it's a small piece, you can replace it. So it's like a Lego system. So actually from these things, we can learn from it, from the past. Even here from the stone master builders in the churches. And these things have not been written down much back in the days, right? So this static graphics only comes up in the 1700s. It's quite late. But these people already built buildings 100 meters high. So some things they did know. Here our friends Guastavino, or even a Roman concrete vault. Wait, that's not the right one, but okay. Once you know actually how people build tacitly and how things work, like from the cathedrals, you could then, because you are architects, you have certain proposals in your head. So once you know how the rule works, you can enlarge it or try to play with it. And once you make it explicit, you can actually try to think about it in an architectural sense. So this tacit knowledge, like for floor slabs, if you know once, if you have the explicit knowledge where the line of forces are, you can improve where the concrete needs to be. This slab from Luigi Nervi is only about 20% of the original slab. And if you think about how you could do this with 3D printing, you could actually already save just on the regular slabs quite a lot of concrete. So this is something, even the robots, because we all the time hear some people say we should be against the high-tech elements, which I find it a bit weird, because all the craftsmen that we know, if you work with timber people, if you work with stone people, the way to go forward in their business is actually to use more technology, to use these robots actually to build for the future. But we have to use them architecturally. Even the tools that you have at your disposal, this did not exist 30, 40 years ago. So these are the kind of tools that you can, they are for free. You even have AI to help you. The calculations on ChatGPT, I would warn you, they are not correct, so be careful with it. So you do need to know a thing or two about calculations before you use ChatGPT for it. But even here, look for the 3D printing. The robot can exactly give us direct information, feed it back, and you know if the wall is gonna collapse or not. So the buckling of these things. So all these tools actually exist and can improve our daily environment. I just want to show this because I don't think that we should oppose the one or the other. We need both if we want to advance. And we talked yesterday still about Pouillon. And Pouillon is typically the guy that made that we can build with stone, of course. And also all these things, it's a slide, maybe not so important, but where the real power is here. Because when we make changes later in the process, it costs a lot of effort for everybody. And we cannot make these big changes anymore. So here in the concept design, if you already have a lot of parameters readily available, if you know how to construct, it can help basically. This slide I will not. And then experiential pedagogy, that's the third theoretical part, I would say, but it's not that theoretical. It's just Amin and myself, we have been able to work with a lot of students in the past. And one thing that we notice is also we ourselves were not trained in making much. I don't know, Amin, for you, but for us it was much about drawing, it was much about... So it's a full world that is very abstract. And I see, and we are a bit lucky in a way, we can have fun also in making things. And we hope, of course, from our perspective, that brings you back closer together with the people that are really on the construction site. Because I see that these people that are very lowly paid, they are not well trained, they have no direct discussion with the architect, with any other person in that hierarchy of decision making. So the guy that is really doing the rebars on the construction site, there's nobody really talking with him except for one boss, and actually every day you see other people on the construction site. This is not a very inclusive society. So they should earn more, they should be better trained, and then we can make better buildings. But for that, as architects and engineers, we need to try to learn also how to build better. Serious? Well, architects are paid badly. That's.
When I was a graduate, commuting to work for my first job, I opened the back of the newspaper where the job titles are, and a rat catcher was earning more than I was. I was thinking, oh my God, I've studied how many years? I'm earning less than that. I keep up with the job description rat catcher to see whether my salary is increasing.
I'm sure in Paris it must be the same. The rat catcher is still earning more than we do, I think. It's a rare job also, so it's not everybody can do it.
It wasn't chief rat catcher, it was just rat catcher. But bricklayers earn more. They're normally in demand. These people are skilled and in demand.
They're still lowly paid.
Possibly your skills are not so much in demand. But that's part of the issue that we're talking about, which is that it's the responsibility. Responsibility really lies in the Industrial Revolution. Britain in the Industrial Revolution being so heavy with workload and master builders. So all of you would have been master builders or apprentices to master builders, architect in lowercase. But the amount of work that was going on, there was an inevitable specialization. So the first people to specialize were the people who did infrastructure, engineering, and they became what's called not military engineers, but civil engineers. only a couple of years later, those architects who considered themselves architects with a capital A, we've done the studying of the classics. We've gone on the grand tour, decided to specialize too. And they're the ones who changed the teaching system throughout Northern Europe, that eventually became the teaching system throughout the world. From now on, none of you, they actually banned the idea that any of you should learn with your hands. Yeah? So before then, you spent 7 years learning with your hands, from sweeping the floor, visiting quarries, visiting timber mills, knowing the latest materials. And after 7 years, you can imagine, after 7 years, you know the cost of things. You know the structural capacity of things, as well as if you've done your reading, you know how the classical forms of architecture work. That was banned, and from then on it was just drawing, and that's really where we are still today. Most of it's drawing, some people are experimenting. How do you augment that knowledge again to make that difference? Well, your melding of our two faces is sort of part of the story. You have to now, right from the beginning, have an engineer next to you and the architect, as well as the maker. So we talked about those different materials. Those different materials are now in the hands of specialists. Specialists in timber, specialists in stone. Never draw something and imagine, oh, it's beautiful, somebody else will make this for me. Because what you'll find, just like those initial cartoons, as soon as somebody has to make it for you, why would the architect draw this? Well, mostly because you've got no idea how the structure works. So you've drawn something that is not viable for a private house. Yeah? So if you sit down with the people who actually make this stuff, right from the beginning and say, with the engineer, I've got this fantasy that the house is going to look like this. What materials you're thinking? I don't know, you tell me. Okay, maybe if you want this special shape, you use the following materials. And with the engineer, yes, the roofscape or whatever is possible. So yes, carry on playing and learn from that play. Ultimately, hopefully, during your education process, and then certainly as you graduate and work, enmesh yourself with the engineer and the people who make.
I think that the problem is also engineers, when they do their studies, mostly they don't get drawing courses, seriously. And so sketching is not, so the way how you analyze certain things in your projects is by sketching and doing things. That's not in an engineering course. Also, the history of architecture does not exist in courses in engineering. So I think it's very weird that you have to split it up so far to then do together a building. And this creating a common background is also very interesting. And I think we can find it partially, like for us, in materials, but also in this experimenting. So this is some work in Versailles. We test with some straw, and here in London, where I was teaching this workshop, also with pre-stressing stone. So we just continue actually to experiment. And I think this is something that is open to you, learning by prototyping. And why I show this as well is also for buildings in the future. People have over centuries prototyped their ways to new buildings. These churches and the way how the master builders in France in the 1500s were doing things, or even Brunelleschi in Italy. See, they learned it by doing and prototyping. Now we have a code telling you you can't do it anymore. And I think it's limiting ourselves. We can only get past it by prototyping, in my opinion. So this is just around the corner, actually. So what is very strange, but you have the Compagnon de Devoir just around the corner. You were aware, right? Okay, you sometimes see them, or? Okay, brilliant. Well, here it was interesting because was some students from Versailles working with them. People come from such different backgrounds, and hearing them discuss together, this is really where we can actually improve our skills also. I flip through it quite fast, because then we want to come to the topic of the day, actually, yeah? About stone. And I think you have this wonderful slide to start with.
So you remember the slide with the forest, yeah? And people worried, oh my God, we're going to run out of wood. Well, not if you farm it sustainably. It's the same with stone. Often people say, well, surely we're going to run out of stone. Yeah. Hopefully you can see from the slide where I'm heading. We're never going to run out of stone, are we? Yeah. How many of you still boil milk? I know most people don't. If you have a pan of milk and you leave it for a few minutes, it's got a skin, hasn't it? A cooled skin. Yeah. If you put your finger through the cooled skin, it's still boiling, isn't it? Well, we live on that cooled skin. We're like microbes, never going to get through that cooled skin. The rest of it is just boiling, waiting to come up to that surface. So we're never going to run out of stone. Don't worry about it. The world will be covered in quarries. Well, again, this is Europe's largest quarry. Is it in Europe's smallest country? Sorry almost Europe's smallest country. It's in Belgium, yeah. Europe's largest quarry. Nobody can see it in Belgium. It's not that big, is it really? Yeah. Now, people forget steel. It doesn't, you don't pull a piece of steel out the ground, do you? Look how many quarries it takes to make steel. That's the list of quarries, and then you have to burn it to make the steel ingot before you then use even more energy to turn it into a beam or a column. Okay? Cement. Did you know that cement was made of stone? You take limestone and you smash it to pieces, mix it with other quarried materials, and then you burn it again. And that's just the cement, isn't it? It's no use on its own. You then have to mix it with more quarried materials. That cement, turned into concrete, is now 40% of the strength of the original piece of stone. And how do you make it stronger again? You have to put steel in it. You have to reinforce it, yeah? So you can see, in that logic, it seems a bit absurd. Today it seems absurd because we have a lens of embodied carbon. France obviously has a long tradition of using stone. You know Fernand Poulenc, I guess, yeah? Okay, yeah. I mean, he's only a sort of recent hero in the UK. But you have also a sort of tradition of crucifying your heroes, don't you? So poor old Fernand Poulenc, the tradition of stone was killed off with him, wasn't it? By you guys. Brick. Yeah, so brick became very popular in the UK more recently, in the last 10, 15 years. I dare say we blame the Belgians, because before then it was multicolored cladding, plastic cladding that was highly flammable. But now we have brick. Again, multiple quarries, burnt, and we come back to stone. One quarry, no burning, just cutting, processing, and obviously timber. And you've gone on to a lovely facade.
Yeah. No, I think some slides back to put it into perspective what you said also. No, the choice is actually not so complicated. The knowledge is here we are in France, so we're talking mostly about France, but for France this should be, and you're getting taught in it, when we could ask ourselves, is it a modern material or not? It has been around, so we can actually do pretty much with it. And so the quarries, the geology is all present. France has a rich tradition. There is actually in Europe, and I went recently to Pakistan, I went recently to Kenya, I went to different other countries where actually there's still quarries going on. The knowledge is actually pretty much around. So we've been using it for quite a long time, at least since the Egyptians. They put just big blocks. They didn't know how to put it smaller, but I think it has been around, so we can do something with it. It's quite massive, no? I mean, you have to be, it's the technology of running a quarry is quite interesting, and there's much research in it, if anybody is interested in that. There's different cutting technologies. There's also ways of reducing the carbon footprint of cutting it either through the energy, but also to go into the mountain rather than have an open quarry, all these things. So, and these are some of the machines that have allowed us in the last 60 years also to go faster with this. And this is typically because why I think Poulenc is now also famous in Great Britain. He was a liberal, right? He was very open to have a lot of money. And he was putting up businesses, so he was a businessman. And I think in architecture circles, that's not necessarily the thing you bring together with an architect. Although, and I'm sorry to tell you this, the most famous architects are actually pretty good businessmen also. So mostly they do survive. You're not going to get much courses about this, how to run a business, which is a bit weird also as an architect, but that might be the stuff for another lecture.
Yeah, I mean, it's very strange because this is the language of your clients. Whether it's public money or private money, it's money. Somebody has taken it from the bank. Very, very few clients. I think we have one client every 10 years who has just money in his pocket so much they don't know what to do with. Yeah? Everybody's borrowing money, and they're borrowing it for a time period, and that time costs them interest. So you need to make key decisions quickly, and the reason there are other consultants who do that for you now is because most of us are educated stupid. Yeah? We don't learn anything about money. Oh, give it to the cost consultant. Give it to the project manager. I will make sure the architect makes these key decisions by this date. Otherwise, the client will lose money. So you need to try and appreciate that. And if you're not being taught it, or I wasn't taught it certainly, you learn through practice. Learn it. Learn the language of your client. So the best way of expressing this to students, because when I was a student, most clients you imagine, they're really rich people. Why do we care about their money? Well, they're not all like that. So if you have a client who's making housing that are taking people off the street. So we have a client who had a charity. Their responsibility was to take people off the street and build as much as they could to take these people off the street. We found a method of building that was 25% cheaper than the cost consultant was saying was the standard building cost in London. But the project manager and the cost consultant was saying, how can it be possible? How can it be possible that it's 25% cheaper? Surely the architect doesn't know what he's talking about. It's a risk. Don't do it. Spend the extra 25%. So we told the client, look, your responsibility is to make more housing. For every 4 houses you build, you'll now get one for free if you do this method instead of the other method. So they made up their mind. They're going to build cheaper, and they did. So it's important to know your client, the language they speak, which is money really, yeah, because that will drive your architecture and define your architecture. Your ethical decision, yeah, in the same way that embodied carbon is your ethical decision.
Yeah, because this is the problem we face with building with these expensive materials, because that's the thing that we... Does it work without a mic or not?
It's for the recording.
Ah, for the recording, okay, sorry. So, but how to make it really that it works? So Pouillon was one first, actually, by detecting new machines and all this to make it much cheaper. So that's really the big problem. So these are some of them, and so why we show these about geology. If every project you do, if you want to go into it and you want to know more about it, usually you go through the history of the materials. So that's why usually we show these slides. It's about the geology. Where do you extract it? Where is it present? How is it being used? What is the benchmarking? What are the machines that I can tool it with? So basically, it's really checking what are the different stones, what are their capacities, how can I work with it, where are they based? So this is even made, I think, from Thibault and his team at some point, but there's in France quite some knowledge about where to find it. So this is all things, even for Paris, it used to be a big quarry, right? So most of Paris has been built out of Paris, which is a bit of a problem. I don't know if you're aware, but you have to, normally if you build in one of these zones, now they ask the private clients to fill these holes and pump it full of concrete. It's brilliant. We will have a massive socle in concrete that we can probably cut out as stones again some 1,000 years from now. Not sure about it, but okay. So anyway, I think there's some knowledge. So learning from the past, tacit versus explicit. There are things, again, there's so much knowledge about this already present. Pouillon was here. So again, learning from the past. This is about 12 years ago. It's dry stone for a vault of about 20 meters. It's only 8 centimeters thick. So it is possible, learning from the past, it has been done. So we are able to do it, we just need to scale it up sometimes. This one here is in the UK, King's College Library, 6 centimeters for 12 meters of span. It's thinner than an eggshell. So it's actually quite good. So we can learn, and honestly speaking, so the godfathers of concrete in France have all been taught by this guy. So it's Paul Séjourné, who was a professor at the Ponts et Chaussées, who had Albert Cacot, Freycinet, all these people that invented new things how to improve concrete were his students, and he was the last one in Europe, more or less, to build the biggest bridges in stone. He has some very good books on how to work with stone. So it's all there, it's all there. And if you ask to redo it, people say, I don't know how to do it. This is only 100 years ago. So it's not very long ago. Huh? It's, and these things, well, I will not go into the exact methods because that would bring us too far. So this is the usual method, but it means that you as an architect can really do this. It doesn't seem so complex, does it? So it's just graphic statics, it has been used. So the methods are even actually pretty open to everyone. So if you look at all these things, we could use it again. And if you look at the future, because then Amin, I took your slides here, and this is where we are today, right? People using stone, most of it is for cladding purposes. And I think you took some slides from the UK, how it works there.
Yeah. We have to use the mic apparently because of the recording. Okay, so I mean, yes, this is how we build in stone, but it could be anything. You just have to walk towards the station and you know your concrete currently has a pretend wood facade. Has anybody seen that? Directly opposite the station? You can replace anything, so it's called a skin, a weathering skin, because all it's doing is stopping the rain hitting the insulation. I've now offended them. I'm kidding, I know you guys have to go. So that's the way we normally build in stone. Is there anything wrong with that? Anything wrong with that? Well, some of us might just look at it and aesthetically, personally be offended. But look, here's the superstructure. Here is a clamp on one side that picks up the clamp of the facade system that has to go through the insulation, the vapor barrier, and if this was steel, fireproofing. 1, 2, 3, 4, 5, 6, 7, 8 different layers, different processes, different energy, all adds up, plus different trades, so different laborers. Each one of them has to take a liability. So there's opportunity for failure as well as cost and embodied carbon. So I mean, this is the UK, this is buildings just around the corner from our office. You can see there the brick where what would have been explicit teaching of how to build. These would have been piers of brick or stone holding up spandrels that then hold up the floors beyond. But no, somebody's put up a steel frame and exactly the same bricks that are perfectly capable of holding up the whole building are then being suspended on every floor, slowly built from the top downwards like a curtain. Yeah? And if you look carefully, in some areas, the slide's a bit dark, pieces of plywood with skins of brick glued to the underside. Because the practice has got graduates in who've modeled it in 3D, pressed a button, brick render, all over, yeah, including the underside. Is there anything wrong with that? Well, eventually it just falls off, doesn't it? If you're gluing brick to pieces of timber, eventually it's just going to come off. But by this stage, more than 12 months later, the builder, their liability is finished. So ultimately it goes back to the architect or the engineer. Did you pass this? Try and avoid it. Try and learn your materials. I mean, luckily nobody was killed in this one, but you probably know the UK is currently going through its crisis of making things as cheap as possible, architects lowering their fees so they're not really looking at drawings anymore, asking somebody else to look at it, and of course we have buildings that burst into flames and kill people, as well as this sort of business. So, in stone, we were asked by Canary Wharf, one of these large development companies, is it possible to build in stone for our typical, most optimum office building, 30 stories tall? We didn't know. We worked with some structural engineers, sustainability engineers, and cost consultants, and you can see there Let's start with scenario 3, which is the steel frame, high in its embodied carbon. Concrete, reinforced concrete, is better than steel. And then all stone, floors and exoskeleton, less than half of the concrete. But that mixture of stone and timber is carbon negative. Now, I'm not sure whether you're allowed to count carbon sequestration in France. In the UK, you can count it if you write a piece of paper, a legal document saying that the day the building is demolished, so it stays like a covenant on the property, not with the landowner, the developer, but on the land, saying the day the building is demolished, that timber or the material has to be reused, yeah? So it's not just thrown into landfill. So that allows the reuse and locking in of that carbon. Does that make sense? Good. Now this is 2019, we did this study, and since 2019, you can see there, this is me repeating, know your client's language. The cheapest version of this exercise was actually the mixture of timber and stone. Why? Now, a cost consultant doesn't know. The cost consultant has a book. It's actually got cheaper still now. It's even cheaper now. That's 2019. Cost consultant doesn't know. Yeah, the cost consultant assumes everything is built as is usually done. You've used stone and you've used timber as structure. Okay. Amin, it's coming out more. Why is it coming out more? Well, you still have to clad the stone structure. Well, what am I cladding it in? You're cladding it in stone, aren't you? No. And that's because they have a cost plan book. You explain to them, take out the cladding. The stone is the structure. You don't need to clad it. You don't need to clad it outside. You don't need to clad it inside. It is fireproof. It performs better in a fire than steel or reinforced concrete. Same with the timber. People like looking at the timber and they like looking at the stone. As long as the timber is deep enough for charring, it performs well in a fire. So you can strip out all the extra layers of plasterboard, fireproofing, and so on. That's why it becomes cheaper. These are exercises for another developer in London. So this is about showing them, this is not our design. This is saying you have already got an architect to come up with a beautiful elevation of a new street. All of it is BREEAM, diamond, outstanding, but built with a steel frame, aluminium, all the red areas in that menu of materials. And he's asking us, how is it I'm getting diamond? Can I bring that embodied carbon down? So this is how they're doing it, normally steel or concrete, exactly as I was explaining before, everything is suspended. How can you make it differently? Well, we've been working with engineers, and Klaas knows this system, which is basically taking floors, beams, and columns, not as massive pieces of stone, but if you like, shish kebabbing them. You drill a hole through them, you tighten it, and it becomes a pre-tensioned column, beam in the yard that you can transport, lift with a crane, and bolt together just like a steel frame, except it's 99% stone with a piece of steel that runs through it. Or timber structures with a stone brick facade, sorry. So you can see there, the stone, people forget, you can cut stone into any size you like, including what looks like a brick. But instead of firing it, any color, you can replace the otherwise fired clay brick. These are permutations on the same theme, showing how you can drop the embodied carbon of that typical construction system. So this is, again, for the same developer. I don't think you're going to, I think I'll have to go through these at a pace because you're not going to remember all these figures. But you can see if you have all concrete solutions, how you then, if you, even with a concrete base and piling, you can then replace it with timber, and depending on the height you go, begin to substitute it with stone or clad it in stone. This is a system that shows you that column, beam, floors, all this is stone, yeah? Even the bricks are stone. So they're being cut. So a bricklayer doesn't look at it and go, oh, what's this? It's a special, I don't want to lay it, or I have to charge you extra. Here it is exactly the same size as a brick. It looks like what's called London stock brick. but a fraction of the embodied carbon, 98% lower in its embodied carbon after cutting it down to brick size, yeah? Same price as a brick. Why would you ever use a 5 clay brick again? Anybody? Anybody come up with a reason? No.
Because
exactly.
Because the Belgians live of it.
Because you are evil Belgium. There is the system where you can see at the end are some metal plates that you fix together. So if you're in a seismic zone, for instance, and this structure wants to move, the stone is doing fantastic in compression, but it's absolutely no good for a movement, yeah? So what you do there is make your fixings like a bucky joint. So the end is metal, while the rest of it, you can see there the threads that go through, is stone.
So we're moving into real examples now. I think we get there, slowly, but really. It's like with stone, it takes a bit of time. Just with these, I think this is the stonemasonry, where this was set up. So these are magnificent guys, and they are all called Pierre or Alex. It's like, otherwise you can't work there. And they're all French, because they've all studied, so it's in Great Britain, but they've all done their compagnon in France. And recently my son did an internship there. He's never going to do it again. He had to cut a little octagon, and it took him 2 weeks even to do half of it. It's really a job to learn. You need 5 to 7 years to really become a stone master. So it's not really just a simple job. And they are really good, actually. So if you have the chance to work with them, it's really interesting. So let's go to the projects. And so we start from a bit smaller to a bit bigger. We choose not the most, like, it's also housing. It's really the market where we want to see things happening. And it's a lot of testing. So the first one is really small, a little pavilion in front of the Château de Versailles for Chartier d'Alix, where the idea of Chartier d'Alix was to have a green wall in front of the chateau, a circular pavilion when you come from the train station. And they wanted to do that exclusively with reused stones that come from the Région Île-de-France. So it's actually stones that were broken once they were used for the roads and all different things. So it's from the technical department of the Région that they gathered these and they cut them to size, basically. And I thought this is a very nice example, a kind of spolia idea, because the pavilion not only got built up here in Versailles, they used it again for the Olympics. Then so they took down stone by stone, so it's dry stone, and that's why you have the thickness of the wall. This was some ideas for the roof. So we had these chips for the roof. Unfortunately, they put beams underneath. I don't want to show it. That's the contractor. He was not sure about our solution. So, but this is basically, so you have a certain thickness. You also have the rounded shape so that it actually holds against the wind and the lateral forces. The thickness, sometimes you have a brick that goes across. So it's one inside, one outside, and then some bricks that go across, so that the pressure of the earth actually is diverted and that the wall can hold it up. But you see how they cut it? And I thought it's a nice idea to really talk about reuse, but also dry stone, because stone is mostly a hybrid solution, so you need cement or glue to really put them together. And in the regulations, this is quite complex, because most of the cement that or the mortar that you use to level out the tolerances between the stone, it reduces structurally mostly almost by 3 the capacity of load bearing for your stone, so which is quite a lot. The gluing is much less, but according to Eurocode, you can also only take it up to a certain level. So we have a lot of regulation that goes around these topics that make that we actually build really fast, and we could do it sometimes a bit less. So that's why we constantly prototype these buildings, so that we can change the regulations and build again like 500 years ago, which is a bit weird to say now, but I think this is also a good example where you have your place. I think. There you go. Oh, yeah.
What have you done with it? Oh, there you go. Yeah. The first stone building that we put up, we visited French quarries. The reason that we visited as French quarries, because the French stonemasons, as Klaas was saying, are still trained in what's called dimension stone, how to cut stone out to make buildings. The UK just does decoration and restoration. So they took us on a number of quarries, and some of these quarries only have 2 or 3 men in them. But they're using this equipment with industrial diamonds that makes the stone much cheaper than it was maybe 15, 20 years ago. So we learned about how to cut stone, some of it still in the old way, and then the minimal amount of finishes that you gain when you extract that stone without working or carving it anymore. And sometimes you find, if it's a sedimentary stone, quartz and fossils in it. And then how do we use that as a piece of structure that holds up a conventional floor plate? Testing it, and then deciding, okay, instead of a grid of columns, if we use the stone as a facade, but what's called a load-bearing facade, as an exoskeleton, everywhere there's a column and a beam meet, it's then connected to the floor plate, which means you don't need any internal structure. You just have the core, the lift and stair core, and the rest of your interior can then be free. Free for an office, free for an apartment, free for 4 apartments or a hotel, flexible for its use, and therefore made entirely out of timber. That's us, I think maybe 2014, I think we started, finished 2016. So there are the minimal finishes you gain from the quarry. And if you'll notice there's a gap. So the reason there's a gap, as you can see, the stone is moving because it hasn't been carved up much, just cut simply. That means that it's fairly cheap, inexpensive, and if you put sort of 30% timber, 70% glazed curtain wall behind that, then the water shoots past. You don't need any special sealing of it. Okay.
Sorry, yeah. So this one you can visit actually at the moment. It's under construction. It's in the 14e arrondissement, L'Eau Petit. It's where the former hospital is just around. And it's an interesting project already simply for the fact that it is with 3 architects, which is Kuhn Malvezzi, Nicolas Dorval-Bory, and Plan Commun. So that's quite already exceptional, I would say. And they came up with this concept actually during competition. It was still pretty much all of the vertical structure. We had an idea that it could principally all be made of natural stone. Not the cores, unfortunately, if I recall well, Etienne. Okay, so I have a control from in the office. Now I have to be careful what I'm saying. But in the end, some of the columns that were inside, we still had to move and change them to not naturals, to other solutions. After many iterations, basically what happened and what you will see according to regulations, not all the people trust stone already that much that you can use it entirely structural for carrying all the vertical loads of a building, right? So here the stone is load-bearing for itself at least, and for the balconies, but the floor slabs still have a different structural system. So whenever you visit the site, it's quite beautiful. It goes pretty fast also because the blocks are quite big, so they can go very fast. So here 8 or 9 stories. I will flip through the plans. So if you drive by, I think you can visit the whole site. There's a lot of new buildings actually being erected at the same time. There's also one from Lacaton Vassal, which has not been awarded yet to a contractor, but there's a couple of others that are quite interesting. So nothing special. The floors are all made of CLT. The core is out of concrete. And then there are a mix of bays that are made of prefabricated concrete elements so that the windows can be fit into that. And then there's the natural stone. So what is interesting for us as well is that we go back to this hybrids for constructing also. So usually contractors are not so happy with this way of working because they don't necessarily have all the specialists themselves. But the future of building is definitely much more hybrid than we had these monocultural buildings. So it's a bit of, I don't know if you can really read it well, but what an interesting aspect, so here you see the build up a bit. And what happened over time, so stone, you have to, there's a lot of things like Amin already showed, the detailing is quite important to stone. So if you don't want to end up everywhere with steel again with all these elements, you have to really detail it yourself, you have to check with the water barrier, you still have to check with the insulation, which insulation. Because also, as you probably have heard already, mostly the stone is also capillary, so there is a bit of changes in hygrometrics behind the stone. So the choice of the insulation on the inside, you have to be careful that it's not actually that it doesn't get full with water, right? So you have to choose, I think with which one is it that we use the insulation here? Wood chips, wood fiber, yeah. So, but you have to be careful in the choice of that. And then the other thing that was very interesting learning lesson for us, so you see the beams also, so above the lintels are just cut so that they, basically it's a flat beam, and it's through the cutting pattern that they function as a structural arch. So that you have to know, but the compagnon, they know about all this, but as a structural engineer or an architect, you would have to know about all this as well. So you have to plan all the individual blocks also. So you cannot just let it decide by anybody else, you have to be there. And you have to check which machine they have so that you don't take a block that is weighing 2 tons, because the guys, they cannot handle 2 tons per different block, right? So the block size does have an impact on the speed, but it also has an impact on the cost. The smaller the blocks, the more you need to cut, the more expensive it is. And the bigger the blocks are, the more complicated it is to find a block that has the same quality over the whole length of the block. So if you would take a block of 8 meters, it's not that it doesn't exist, it's just very difficult to find a block that has the same exact properties all over these 8 meters. That's why we cut them up in smaller pieces. And then what we try to do to reduce prices is to choose blocks that are a bit less dense, because they go faster in the cutting. So everything for the price is in the cutting process, well, much of it. So in the south of France you have blocks that are less dur, so you can cut them more easily. The ones that are up north and closer to Paris are a bit harder, so they cost more, and usually you would put them on the bottom part of your building. Say you want a wall that is 30 centimeters all over your building, 9 stories. Since there's more loads on the bottom of your building, you would take the stronger stones and the less strong stones up on the upper floors. So this is what we planned, and then again, as what I told you, this is a hybrid construction. It's the cement is also in this calculation. So you have to calculate the mix, and the combined mix between the mortar and the stone. Let's say you have a stone of 50 MPa. If you then have to calculate with a mortar that is only 10 MPa, basically the whole thing goes back to together 14 MPa, or even 10. You have to take the lowest value if I'm not mistaken. But in any case, it's a hybrid. So you can have the most fantastic stone, but you're depending on the weakest material, namely the mortar, which is a bit, yeah, you have to be careful with that, because here in the end, what we ended up with, instead of using the more expensive blocks to have enough rigidity for the building, the contractor came with the idea, if I change the mortar to a very high yield mortar, then I can actually up the value of all the stones, and then we can use the less expensive stone for the whole building. So this is a kind of smartness that you also need from the people on site. It was actually quite good. So we could build it cheaper. And it's still a social housing project. So I have to say this is quite fantastic. I could not imagine another place than France to build social housing in natural stone. So this is the cutting pattern. So this, you have to work on it as an architect and an engineer also, because it really has an impact on the cost, on your aesthetics, on the structural viability of your whole project, basically. So this is the constituting elements. And you have to go into the detail, whereas in France we don't necessarily make the execution plans ourselves, but you have to go and imagine yourself to go quite into detail. So this is how they do it. And be careful with this hook. It's still the same machine they were using in the 1500s, actually. It's pretty much, it's more electrical now. And these guys have to be careful that their fingers don't get into it, which happened on the construction site once. But he didn't lose his fingers, no? So happy, so. But it's a dangerous job, construction. So here it's quite beautiful. They are storing, they have to be careful also where to store the elements, because the CLT slabs, of course, it's quite a weight that you would put on it. So this is more or less where it's today. It's already a bit higher. Then I let Amin.
So within a couple of years of finishing Clerkenwell, we were asked to have a look at this on Finchley Road in central London. So this is the frame system again, but what we learned was that instead of concrete floor slabs, we split the building into 3. It actually worked out to be cheaper than infilling this with construction and leaving the escape core in the middle. And the floor slabs then CLT and internal wall CLT. So really you've got a basalt stone frame, because again, choosing your stone has different consequences. So limestone, you would have to have 4 times the amount of limestone to last 2 hours in a fire. In the UK, once you go over a certain height, the structure needs to be there for 2 hours while firemen are putting it out. So basalt is a quarter of the volume of stone you need, so it's a quarter of the price, quarter of the transportation, so on and so forth. That's it going up on temporary props, and then eventually the basalt, again, a prototype before we erected. This is, yeah, there we go. So, I mean, you might have a look at this. So, maybe 4 years ago, I was at the Royal Institute of British Architects doing a presentation for the 6 best buildings that year, one of which was going to be chosen as the best building in the UK and get the Sterling Award. And the 6 architects were in front of an audience, and I asked them, what is the embodied carbon of your building? Does anybody know? All buildings were made of brick, red brick, yellow brick, you name it, brown bricks. Nobody knew, yeah? Nobody knew the embodied carbon of their materials. They didn't know the embodied carbon of brick. They didn't even know that brick, stone, could be cut into brick sizes. I asked a quarry in the UK, how much will you charge for cutting a stone into brick size? It's actually a French quarry, although owned by this Canadian company, Polycor, who did the first cutting. Then afterwards, all these other quarries came in. Now, can you imagine, in the UK, we buy 2.5 billion bricks a year, new bricks every year. And nobody, not a single quarry, was cutting stone to brick size. So not a single quarry had a toe in the market of bricks. Now, all these, so that's 4 years ago, all these already, and I think we've added to this list, are now entering that market in the UK. Imagine that. I mean, this is the market of billions of pounds that they hadn't entered. And just remember, obviously, the stone is a fraction of the embodied carbon. Comes in any color or texture you like. So again, use your imagination. This is, I dare say, you guys are best placed as architects in understanding all the different disciplines that are involved in construction and asking these sort of questions. And there's a brick one. So that was a site in central London that was, the client said, I've spent too much money on the site, it has to go to affordable housing. How do I achieve that price? It's of a height that doesn't require stone to go that tall. So we said, why don't you just make the whole thing out of cross-laminated timber? walls, floors, roof. And remember what we said? Modern construction, you need a separation of your external wall from the inside, with normally a cavity, insulation, and then normally the internal structure, or it's an external structure. There's a separation, a thermal separation. So what you're looking at is floor, walls, and roof as structure, but nothing else. Yeah, what's happening is you've got insulation with a vapor check, a cavity, and then the stone bricks on the outside. Now, when we modeled it first, and we told them that, look, it's going to be cheaper because you don't have to put aluminium with plasterboard, with plaster, paint, skirting boards, dado rails, and all the rest of it. All that disappears. So you're saving on material, you're saving on labor, and you're saving on time. That's how you reduce the cost. When we said that to the client, I told you earlier, the client eventually went for it. But initially, the agents, the cost consultants said, are you crazy? You're going to end up with a timber interior. You know, who the hell wants to live in a timber interior? Swedish people. Swedish people moved in. Actually, just one. But the client said, I had nightmares of me. No one's going to move in. I'm going to fail. But immediately full. And he said, what was I thinking? The timber is much better than the plaster. Because when people move suitcases and furniture, they scrape the plaster, don't they? Look. Well, this is not plaster, but you get the picture. Yeah? You scrape it, you have to repair it, you have to repaint it. Well, the timber over the years gets its own natural patina. The Italian government gave us some money to find out what can you do with tiles, broken tiles, stone tiles. If you cut stone to 10 millimeters, you're going to get a lot of wastage. A lot of those tiles are just going to break naturally. So they've got mountains of broken tiles. And they imagined we were just going to glue them back together like terrazzo and sell them again. And we said, if you're gluing them back together, why don't you put them across a piece of formwork that has its own structural form, so the tiles become pieces of structure. Now, we actually did a number of these, but this is the final one where the glue essentially becomes the marbling. We put a bit of pigment in the glue. Internal insulation, so internal face insulation, then external face. It's 4 meters tall. It looks like it could be sort of 4 centimeters there, but you need a person to stand there. This is in Seoul for the Seoul Biennale, but there was COVID, so it was constructed, and immediately there was lockdown. Never saw it. Last thing that we heard was that they had to put it in the bin after they smashed it to bits. But there's a version which is 3 tiles made into a sort of barrel vault, a truncated cone barrel vault. But look, the simplest form obviously is just stacking it, one piece of stone on the other, yeah, and leave it as raw as possible or clean cut. It's up to you. Very, very straightforward. Next, you'll see experiments and pre-tensioning. Can you see that? That is 1, 2, 3, 4, 5 pieces of stone where, remember what I was talking about? You shish kebab them. Yeah. And then tighten the ends. Now, some of those, so this is with the control piece, how we wanted it. Some of those are 18 meters long, because that particular client wanted 18-meter long. Imagine looking up at the ceiling. This is a floor slab, 18 meters long, in that shish kebab stone. Same with the beams. So you can see there's an experiment with a beam. Some of those are 8 meters long. And then here, making these off-site. So these are the arches, ribbed arches, that are then interconnected. And this is actually that lamination that we learned from the Italian research, where we took 100 millimeters of stone, the crust, which is normally waste, crushed for aggregate, put it across formwork, and then joined it again to make a vault that sits within these pre-stressed arches. And that's what it looks like internally. Can't quite, you need people in there to give you the sense of the scale.
I wonder if we should take this as the last one.
Yeah, go for it.
Because we're going on the experimentation, and I think it's a good one to then go to the conclusion. We have other examples, I see. So this one, maybe to go into that. So it's about experimenting, because a lot of things in stone have been done, and so you can learn from the past, we can repeat the past, we can just improve it and actually make it for stories or buildings of 20 stories, so we have to augment our knowledge still again. And what, in that sense, the one step that we went further than before is natural materials. They work pretty much good under compression. Steel works good under tension. So mostly it's true in general for these natural materials. So the pre-stressing, what Freycinet did for concrete, it's only 100 years ago. So he tested a lot with it. It's all prototyping. There was no quote about the pre-stressing. The bridges are still there that he built, Freycinet. But we can do it with stone and just look at it as something like that. And also the tooling can help us again. So here it's a staircase for a luxury brand. It's in New York. And funnily enough, again, on the construction site, all the people were speaking French. So the compagnons that were there were speaking French. And we were lucky also with good friends of Amin, also with the engineers of Webb&Yates. They came in to do some calculations as well on this staircase. But with the office, we try to find the optimum for a cable in this, because usually with the companies that I know that make these kind of crazy staircases, in natural stone, so this is just the railing. Usually, actually, they put the pre-stress in the steps, and so the shish kebab, you just make it like a slab, and then you tilt it. That's about it. But as a structural engineer, usually you would try to use the railing, because that already has a structural height. So that's our thoughts were immediately to do it in the railing, especially because we had a landing in this one, so in the middle. And that makes it geometrically a bit complex, because you have to put cables one and against the other. So it's not so easy for the pre-stressing if you would want to do it through the landing. They have to follow up on each other with complex bending moments. In any case, this is where we used our software skills as well to find the perfect line. We also knew which robots we would be using, because here the panelization of these elements, that's also where we set it out ourselves with the computer already, like that stones would be really nicely compressed against each other. So there's quite a lot of knowledge that you have to do before you can even suggest it to your client. It only took me 10 years with this client to convince him to do a stair in stone. In the meantime, we built 20 others in timber, in whatever, but he never wanted to have it in stone, and so it's inception also. It took me time. Huh? So with this one, so the tools, knowing about your tools, like which machines we will be able to use, having the software and software skills, the understanding, the structural understanding, the thing that the guys, what can they construct on site, this is all comes back to this tacit to explicit, it comes back a bit to the prototyping. And so here, I don't know if you will see it, well, I will not show this, but this is what's happening. So it's under compression on the top and under tension on the bottom. So typically a beam on two supports, and that's where you use the cables. And what happened, what is quite interesting is also, so this is from Webb&Yates actually that we took it. So the cables, we did this whole complex way how to put the cable in, but this is very complicated, because just for your information, the railing is only 8 centimeters thick. It carries over 13 meters, 8 centimeters. This is quite nice. So it's very thin, and it's been CNC'd also entirely with the handrail and everything. But for the holes, to actually make them precise, they were a bit afraid that if we would follow exactly the right way of this cable, what we drew, that it would be too complicated with the tolerances. So they said to do it straight, but it means that you imagine that there's a little bit of tension between the stones on the lower part, so that it can open up a little bit. There's no Eurocode where you can actually allow for that. There's a certain interpretation that you can do in the English and British code, but this is in America. So the nice thing is, if you know the engineer, the other engineer, you know the contractor, you know ourselves, there's nobody else checking. So we do it ourselves. So that's also nice. If you know how and where it goes, you have to write your own story, right? So this is quite important also for you, for your future prototyping. Just take everything in your hands. Don't give it to anybody else. It's it's the best advice I can give you. So it's very simple. These also help that the beams, because you try to compress it, actually they would, it's lateral torsional buckling that it would do. Normally you would need to keep it straight at the top, but still the steps would help actually that it's not swaying too much. So it's also for the horizontal bracing of the whole stair. So they are slotted in with certain steel elements. And between the stones, there's a setting plate in steel, of course, because when you start to tension it, it can be that you crush the stone too much. So you have to be quite precise, which was something we had to learn a little bit on this one. But the result is quite amazing. I'm just a bit annoyed by the color of the stone, because whenever everybody goes in, they think it's a concrete stair, which is a bit, so you hardly see it really, no, but this is all CNC'd. This is like a very whitish stone. We wanted to have a local stone, but since it was polycore, in the end they took one stone from Portugal. A bit a pity. It's 3 stories. Well, shall we just flip through these and then we go to the conclusion? Is that okay? No, the room is like.
Yeah, I mean, it's just you can see there that you can use stone as beams. It's exactly like your staircase, and if you keep cutting out, eventually you get a truss.
Oh, sorry. Yes. So you can the truss. It's possible, and I will show you, because you didn't see that one yet, Amin.
I did not.
No, that's what we're building right now. Actually, it's a truss in stone. But there's one thing where we are a bit less happy, because actually 1 out of 2 could be a cable. You know, there's one under compression, one under tension. But since it's a bit in cantilever, it's not a very, it's a bit of a hybrid. So we're
interesting. Yeah.
But it's ongoing, so it exists.
You can, yeah. I mean, here it's the same technology, but also making use of a building that was already on site. So making use of some of the old materials we found on site, plus then the rest of it's timber. Upper Street is nothing to do with stone, but it's all timber. Timber with a load-bearing twin wall of a sort of terracotta cement mix.
Sorry, I'm going quite fast.
No, go for it. Yeah. So there is choosing your material to tell a particular story. Obviously, this is a reconstruction of a bombed World War II bombed site. It was just reconstructing what had been there, but because there was a desire by the local politicians to rebuild it. And we were saying, well, the desires for monumentalizing the past are flawed. Therefore, let's pick a material that is flawed, and in the detail you can see those flaws. But feel free to carry on. The rest of it is then in the new inhabitation of different floor levels is entirely in timber.
I will not show this one. It's Gilles Perrault. The construction site should be starting soon-ish, and it's in a. I wanted to show it because it's in a seismic zone, so it's always a bit complicated, and we tried to develop our own tools to make it faster also. So we developed with the team a new calculation method for this kind of buildings also, so that you could go faster. And these are not around, so there's new regulations being made at the time that we are speaking. So research also with our team internally, with the French state, they are much interested that we update our calculation methods. So, and then I think what we want, at least what we thought to conclude with is, what is our future or your future? It's really that you used the word already, the master builders. So what is a master builder? It was not the engineer and somewhere else the architect, it was engineer and architect together. And also the value, so I think this is one for us that is a lesson to take with us. It's also to prototype and really combine old tacit knowledge to new knowledge. So this is a competition for doing pre-stressed beams also, so you showed already real examples that are being built. So it's knowing about the old, going for the future and prototyping. And this is also the future research. Look, this is in a children's school in Portugal, where we did some pre-stressing with some kids. It took them 5 minutes, they tested it, and then they made a big one of 10 meters. The 10-meter beam is only 28 centimeters high. We stood on it with 10 people also. So it's not so complicated, but this professor is quite crazy, so he makes his own tools, the one with the helmet, and he's just testing around all the time. But then it has to find its way to the construction site. So we all have our role to play, but we will have to do some prototyping in real time on real buildings and use the power of each of them. And I took the last picture of your office standing on something.
Well, yeah, it's another one of those beams. I think it's 12 meters long or something, maybe 16 meters. Yeah. Unfortunately, there's too much rubbish in front of it, but otherwise, yeah, it's up in the air.
Thank you so much. Maybe we have just one question because we already are out of time.
Thank you.
I just had a quick question on the environmental impact that stone actually has being extracted. Because you're talking just about the carbon footprint, but it also has a footprint on land. Is there a way of calculating that or taking it into account?
Yeah, I mean, that slide I showed of if you're comparing it with, that slide I showed with where you're comparing it with, say, steel, cement, reinforced concrete, brick, one quarry, one material, stone, while you have 11 quarries for the steel. So you know already, we're not trying to eliminate steel, but if you, instead of having a steel beam, you go for a steel thread for pre-tensioning, you're lowering the demand for steel, and therefore the demand for finding more quarries and more quarries. All those 11 quarries to make the steel, instead of opening up 11, you're saying, okay, I'm using one quarry for stone. So you know that there's already a small amount. We did a calculation where we said, okay, look, the UN expects so many millions of houses to be built every year. You have to remember the developed world, so let's call it the Northern Hemisphere, is expected to add another 25% of construction to what we already have. You know, when we do these talks and you talk to lay people, they often say, aha, stop building, maybe that's the solution, don't build anymore. And you ask those lay people, where are you going? You know, this is normally in London. What are you doing after your lecture in the evening? Well, I'm going home. Where are you know, how are you getting home? By public transport. Going to a flat that is secure, warm, has running water and toilets and the rubbish is collected. Well, there's plenty of places around the world where they have none of that. And that's going to be more than double of what we've already built in the next 50 years. And when we travel, we get told, whether you're in South America, Africa, Middle East, we want progress. We want progress just like you guys. Steel and concrete. Stone is primitive. It's the past. Compacted earth, timber is primitive. It's the past. So one, just for our own purposes, that 25% that we're expected to build in the next 25 to 30 years, needs to have a lower embodied carbon. So the more that we can collapse the steel and the concrete and use stone, that's great. But to answer your question, we did this exercise that if we're housing those people every year, how much stone do we actually need? And it's like a kilometer by, I can't remember, like a few hundred meters deep quarry if you wanted to do one, yeah? So it's not a lot of stone, but obviously at the moment they tend to be pocketed about.
There's a lot of research also on the carbon footprint of these quarries, like which energy are they using? Can you reuse the quarry afterwards? So there's like the repurposing of these things, and they become natural environment pretty fast actually, because the water stands there. So if it's an open quarry, it can just become a forest or something. So you can say it denaturalizes the normal terrain, but okay, we do that with all the rest as well. So.